So, thank you. Happy New Year. It's the first iCafe for 2022. And it's a great pleasure to start the new year with a very distinguished speaker. It's an honor for the iCafe of the Hellenic Mediterranean University, the Hellenic Mediterranean University and the iCafe community to have with us today Professor Elvira Fortunato. Professor Elvira Fortunato is one of the most distinguished scientists in her field and in general regarding, the figures, the performance, the funding that she has received, and how much through her research, her university has been advanced in one of the top research universities, the new University of Lisbon. Few things about Professor Fortunato. She's a vice rector at the new University of Lisbon and the director of the Materials Research Center, CENIMAT. She's a pioneer European researcher in the field of transparent electronics based on oxide semiconductors. She is the co-inventor of the paper electronics concept worldwide. Her work has received more than 31,000 citations and her H index is 79. She is an elected member of the Academy of Engineering, of the European Academy of Science, of Lisbon Academy of Sciences, so many distinctions that it will take us 45 minutes to read it. So for this reason, and thinking how busy and how much involved it's in a many projects, it's a great honor for us, and we would like to thank you once again for her positive attitude in whatever we are organizing here in HMU, from summer schools for students, since we together with Professor Kaliakatsos is among the attendees, for conferences, for research projects. So we consider here in HMU, Professor Fortunato, one of the best friends that we have as a university. So thank you very much, Elvira. The floor is yours for the next 45 minutes, and then we're going to have questions with the audience. Thank you once again.
Thank you. Good morning, and thank you for your warm words to me. It is also a pleasure from my side, and since I have time to share what we are doing, and it is a real pleasure to be with you this morning. And also, I'm glad that I'm the first of this 2022. So I'm going to share my screen. Where is the PowerPoint? Is there? So I'm going to talk, let me put this, I'm going to talk about something that we start some years ago in our laboratory. As you know, we work in the area of materials, in the area of nanotechnologies and materials applied especially to electronics. So we work a lot on new semiconductors. And I'm going to talk about transparent electronics and also and try to explain you or to convince you how the amazing revolution that these particular kind of materials have performed. So as it was mentioned, I am a professor at the Nova University at the Material Science Faculty of Science and Technology, and currently also I'm a vice rector of Nova University for the area of research. This is my main areas. So this is our campus. So you can see on the top of the figure we have the Ocean Atlantic. So here this is the campus of Faculty of Science and Technology. Nova University has 9 schools or 9 faculties. All the other 8 are in the Lisbon, on the Lisbon region. And this one is a little bit outside. We need to cross the river. And this is the campus where we are. And also this is Faculty of Science and Technology is the biggest faculty of the university concerning the number of courses, degrees, and also the number of professors and students. In total, Nova University has around 23,000 students in all the areas. And at Faculty of Sciences, we have 9,000. So concerning the key areas we have inside our research center, we work a lot on transparent electronics, also on paper electronics. We have some work on electrochemical devices, on biosensors and microfluidics, on solar cells and nanoplasmonics. And in all these areas, in all these scientific areas, if I may say, we are using as semiconductors metal oxides. So we are using abundant materials and low-cost materials for all these type of applications. And in some cases also we are exploiting the use of paper, of cellulose for some of these applications. Today, I'm just going to talk about transparent electronics, and maybe in a future seminar, I will talk, or one of my colleagues, on paper electronics. So concerning the outline of my talk, I will start a little bit with the history of transparent electronics, the applications, and a little bit where we are. After that, I will talk about the actual needs. I will refer the advantages of the technology that we are using, and also all of these things are related to sustainability. And even we can say that now we are forced to work with the sustainable goals or the Green Deal. But we start this philosophy, if you want, if I may say, since the beginning of our research group. So sustainability was always a strong pillar in our research, in all the research areas we are performing. And after that, I will finalize with some future perspectives. Also, I will refer some new thin film transistors that we are developing with other type of materials, and also other technology processes. So concerning transparent electronics, I used to say that this was a dream that became reality, and this was due to the fact that I got in 2008 my first ERC, advanced grant, on this particular area. And since then, we had a lot of work, not only inside my laboratory, but also in the world. Concerning the history of transparent electronics, I would like to refer one very important paper that was published in 2004 by the group of Professor Hideo Ozono from Tokyo Institute of Technology, where this was published in Nature, where it shows that it is possible to produce amorphous metal oxides as true semiconductor, and to be used in thin film transistors. And this was a huge revolution, because we can use an amorphous material like amorphous silicon for thin film transistors as a semiconductor, but using metal oxides. In that case, it was a combination of indium, gallium, and zinc oxides. The fascinating thing about these kind of materials, since they are amorphous in type of structure, but since they have a mixture of ionic and covalent conduction mechanisms, what happens in terms of the conduction, we can achieve very high electrical mobilities, even by having a disordered structure, because in this type of semiconductors, since we have an overlapping of the s orbitals, the electrons, the carriers, can move easily without being affected of the disorder of the material. So this is completely different, for example, to what we have with conventional covalent semiconductors like silicon. For example, if we make a comparison between silicon, amorphous silicon, and crystalline silicon, we can achieve very high mobilities with crystalline silicon and very low mobilities with amorphous silicon. So this is completely different from this type of metal oxides. And I like very much this slide. It was proposed some years ago by Professor John Wager, also one of the pioneers in the area of transparent electronics from Oregon University. And in fact, we can, I used to say that we are in the presence of a new class of electronic materials. So we are not only using silicon or germanium or gallium arsenide or other types of semiconductors. We are using copper oxide, zinc oxide, indium oxide, gallium oxide, tin oxide, and besides that, we can have combination of these oxides, and we can exploit in a single material different properties, and this is not possible to be achieved, for example, by using only silicon. So this is another great advantage of this type of these metal oxides. And just 2 years after the discovery of these amorphous semiconductors, only 2 years after, we start to have already some applications and some prototypes of displays, because as you know, the target application for this particular material is for thin film transistors to be used at the active matrices of planar displays. So in 2006, we present at the European Materials Research Society. I organized the first symposium on transparent electronics, and some companies and some institutes presented already some displays, some working integrated devices. So here, in terms of the stability, when we are working with the industry, or if we want to exploit our results to the society, and to have products, we need to think on 3 things. The first one is stability. We need to produce stable devices. And for example, here we have an example of thin film transistors based on gallium, indium, zinc oxide, passivated with a polymer, because usually we are working on top gate thin film transistors. And in this curve here, we have a typical IV characteristic. This is the transfer characteristic of these thin film transistors. And even after 10 months, you can see how the devices are stable. So in fact, these type of metal oxides and this type of devices, they are stable over time. The second thing is related with reproducibility. When we are, again, if we want to exploit, if we want to have our results in real products, we need to have reproducibility. And also here in this graphic, these are some results that we got from a large European project. The name was ORAMA. It was finished some years ago. But here we have in this IV characteristic on the left of the screen, 168 IV curves for 168 transistors, meaning that the devices are quite stable. So this is, reproducible. This is quite important. And also here we have one of the first displays using flexible substrates, because another advantage of these materials is that we are able to deposit these materials at room temperature. So this is also another advantage of these oxides. We can use flexible substrates like polymers or even paper or other types of flexible substrates. So nowadays, GIZO, gallium zinc oxide, is already adopted by the industry. We have already some devices that incorporate this type of semiconductor inside the TFTs. And of course, here we have the main advantages. The first one is the high resolution, because we are dealing with transparent transistors, so we don't have a dead area as we have with, for example, with amorphous silicon. The second one is related to the high mobility. For example, just for you to have an idea, the mobility of amorphous silicon is around 1 square centimeter per volt per second, and the mobility of these metal oxides, we can achieve 100. In some cases, 100 square centimeter per volt per second. So we can increase 100 times the mobility of these devices. Also, the on-off ratio is higher, which is quite important. They present a low power consumption and also a low noise interference. And this is particularly important, especially if we are working with the touch screens. So these are the main advantages. Also, if you are interested or if you want to learn a little bit more about this area, we published in 2012 a book. The book, this is not a book with chapters from different authors. All the book is with the work that we have done here at CENIMAT. And also we have a lot of different chapters dealing with materials, M-type, P-type, and also some applications, also a chapter related to paper electronics. But I guess this book has a very nice overview about the work that we have done related to metal oxides within our laboratory. So also I got, as I mentioned, in 2008, an advanced grant on this area. And also in 2011, this project was selected by the European Research Council as a success story, because due to the impact of this project in terms of real applications. So the actual needs, so the global demands. This was a little bit the history about transparent electronics. So if we want to go towards high performance and low cost electronics with sustainable materials, is that possible? I think yes. And flexible electronics is a golden opportunity for oxide TFTs. So this is the actual state of the art, if you want. So here we have a little bit the evolution of electronics. So at the beginning, the volume of electronics was not so high. Nowadays, the volume of electronics is very, very high. So these are some data from Flex Logic. And since we are democratizing and we have a lot of electronics around us, the Internet of Things and all these type of things, we need to reduce the cost of electronics. So this is quite important, and this is also important for us as scientists to try to develop within our laboratories to find the new materials, to find solutions for these, for the actual needs that we are facing in our world. So we are surrounded by the Internet of Things, and also new challenges are approaching, especially in the area of low-cost electronics. And also here I have a few requirements for low-cost electronics. For example, what we are looking for is for ultra cheap and disposable electronics. And of course, in this area, we are looking for printing is a key issue. And if we want to print our devices, we need to produce the inks, we need to formulate the inks. And also we need to have some attention to power management. So we need to have ultra low power electronics and also energy conversion storage devices. And at the end, we need to have, because for all these electronics to be able to communicate, we need to have efficient wireless communication systems, meaning high-speed electronics and also new devices for Wi-Fi. So, and also if we take a look about the sustainable development goals, we need to have sustainable approaches, we need to have low-cost technologies, and at the end, we need to have low-temperature processes. So concerning the need for sustainable approaches, this graphic or this figure was presented some years ago by the European Commission, and this is the list of critical raw materials. You have here the supply risk as a function of the economic importance, but in this gray square, you have the materials that are scarce. And if you take a look, indium and gallium are there. So we need to, and indium and gallium are used a lot, not only for metal oxides, for these, for transparent electronics, but also for other applications. And we need to substitute or try to use other materials in order to avoid the problem that we are facing now. And instead of using indium and gallium, we are also working with tin and zinc oxides. So this is one of the approaches that we are following in our laboratory. And also concerning the need of low-cost technologies, of course, for example, here I have a comparison between a conventional microelectronic process using photolithography with a comparison with the printing process. For example, just if I want to print just or to have a pattern, I want to pattern a line, a single line. For example, if I compare a conventional photolithography process, I need to have 6 steps. And if I use a printing process, I just need to have 1 step. And of course, the gains are enormous. And also the gains not only related to the environment, but also related to the cost. So we can reduce the cost by more than 60%. And also the waste, because we are not using vacuum systems and also we are not using photolithography. Concerning low temperature processes, here I present some data that we published also in 2016. This is a little bit the evolution of thin film transistors deposited by solution process. And also I choose only TFTs with mobilities higher than 1 square centimeter per volt per second. So just for some of you that are not very familiar with these type of devices, the mobility is like a figure of merit for these transistors. So we are looking for high mobilities and also high speeds and more rapid devices. So this is quite important, the mobility. So in 2007 and 2008, we start to have some devices, some thin film transistors using based on a solution process. And of course, if we start to, instead of using a physical technique like sputtering or evaporation, of course, if we are using a solution process, we need usually to heat the substrate, since we need to promote all the chemical reactions, we need to evaporate part of the reagents we have in the solution. But what we observe in this figure over the years is that as we are over the years, we observed a decrease in terms of the final temperature that we need to use. And if I compare the same devices here, and instead of comparing the temperature, I compare the mobility, we observe an increase in terms of the electrical mobility. So what we observed in the recent years is we have a shift from physical processes to chemical processes, because of course this is the cost is much lower. And also using a solution process, we can formulate the inks and we can use a printing process, which is not possible using, for example, a physical process. And simultaneously, we observe a decrease in the temperature and we observe an increase in terms of the performances of the devices. So we are improving all the type of reactions we are using. Also, we are using alternatives to temperature and so on. Now I will explain you, I will show you some examples that we have done at CENIMAT only on solution process. So here some examples on in this case, some examples on zinc tin oxide produced by sputtering, just to showing that we are not using gallium and indium. It is possible to use other semiconductors, other materials, and this was done at 180 degrees, which is compatible with the use of flexible substrates. Also, we are doing the same by using a chemical approach. Here is, we have thin film transistors based on ZTO by Sol-Gel technology. Of course, here we need to use, at that time, still a moderate temperature around 350 degrees, but also the devices are stable over time, which is quite important. And in this case, they are not encapsulated. So again, I'm using a top gate structure and the device is not passivated. Other examples of GIZO, since GIZO was the first material adopted by the industry, we try to mimic the same, to use the same material, but using a solution process. Here, also some examples of GIZO done by a simple method, by spin coating. And since we are looking for always to try to reduce the deposition process, the temperature deposition process of these materials, we follow a little bit the approach that was proposed in 2010 by Professor Tobin Marks, where besides using a conventional sol gel process, they use a combustion reaction. And by using a combustion reaction, we are able to reduce a lot the final deposition temperature. And if besides the combustion process, we add an extra source of energy like UV radiation, we can even decrease the final deposition process. So here are some examples of TFTs where we are using, besides the combustion process, we are using also UV radiation simultaneously in order to reduce the total budget, thermal budget of these materials. So here are some examples of some flexible devices using this type of process. And here just an example from a company, Evonik, where they present, and also this was in 2017, shown at SID conference, but the particular thing of this display, it was all the layers that we need to produce the display have been printed. Also here, other examples of devices and other applications where it is possible to use these metal oxides. For example, we are using this was a collaboration with the Bologna University in Italy, where we are using this for X-ray devices, also here for other type of detectors. Also here, some examples of high resolution displays using this type of technology. And for example, for a display, to build a display, this is rather complex. For example, we need to have 13 layers, it's a 13-layer process. And we achieved this at a very low 180 degrees, which is compatible with the flexible substrates. And since we are working on new semiconductors, so we are able to produce several integrated circuits and different for different applications. And here a large set of other devices, inverters, current mirrors, and so on. And also another example, and this was these are the results that also we achieved within an European project, 1D Neon project that was coordinated by Cambridge. And the idea was to integrate all these type of electronics on textiles. And we achieved this type of objectives. So just to give you a flavor about future perspectives that we have in place in our laboratory in the area of transparent electronics. Also here, some examples. As you know, these type of metal oxides, they are N-type. It's quite difficult to have P-type metal oxides. Usually they are not stable over time. And if you are looking for CMOS application, it's quite important to have P-type and N-type semiconductors. And what we are doing also here at our laboratory, so as you know, perovskites are used a lot for solar cells. We achieved huge solar efficiencies higher than 20% in a very short in a very short period of time. And also, since these perovskites are semiconductors, why not to use these materials for other applications? And in fact, these perovskites, they are P-type materials. And here we present you an example of the use of these allied perovskites on P-type TFTs. And we achieved very nice mobilities of the order of 30 square centimeter per volt per second at a low deposition process, 150 degrees. And also these devices are not encapsulated. And also one of the advantages or one of the drawbacks of perovskites is the stability, is the reaction with the ambient conditions, especially oxygen. And we performed these TFTs, and the process of these allied perovskites was done not inside the glove box. It was done in ambient conditions. Also here we process these P-type TFTs also on flexible substrates. Also, we perform some mechanical tests just to evaluate how they work after some tests, and they work quite well. And also here we have a comparison, a little benchmark in terms of the comparison with other devices, other TFTs done with similar materials. So concerning future perspectives, also nowadays I'm running my second ERC on metal oxides, and not only restricted to metal oxides, but the main idea is again, and following a little bit the actual needs and the sustainable goals, is try to use other technological process for produce the materials. And we are using nowadays lasers based either on CO2, UV lasers, or IV lasers or UV lasers. And we are able, for example, to build graphene out of polymer or out of a piece of paper. So it is possible in a very low cost and simple process to transform the surface of a paper, of cellulose, or polymer. In this case, it was polyamide, and we transform the surface of the material into graphene, and simultaneously we pattern the lines, in this case the electrodes. So this is very easy, because just by using a laser we draw the electrodes and we transform, we synthesize, and we build directly the material without using masks, without using liquids, without using high temperature. So this is just a case of an example. This was not invented by us. This was proposed in 2014 by Professor James Tour at Rice University. And this is quite important because, of course, the graphene produced maybe is not has not the same properties as the conventional graphene produced by CVD technology, but we are talking about completely a different set of technologies. And this was the case for an electrochemical biosensor for some antibiotics, and it works quite well as electrodes. And also we are exploiting these not only for electrodes also, but for the synthesis of also metal oxides and other type of materials directly on the substrate we want to use. So just final remarks of my talk. So it is possible these new materials, the materials for transparent electronics, these metal oxides, they are not only related to thin film transistors for display applications. We can exploit these new semiconductors for other applications, transparent or not, because this is a material. Of course, for some applications, it is important to have transparent circuits, but for others, maybe not. We can apply these materials not only, again, to electronics, but also to biosensors and also detectors for different areas, memories, intelligent tags, and others. And the use of a maskless and non-vacuum approaches is a promising area, not only to replace silicon in conventional applications, but especially to open new areas of application. So, of course, I would like to thank the team that is working with us. We used to say that in our lab that if you want to go fast, go alone. If you want to go far, go together. And we prefer to go together. This is an African proverb. And finally, I would like to acknowledge the national funds, especially from our research council, and also the European funds, and not only the Horizon 2020, now we are starting Horizon Europe, but especially the European Research Council. In fact, this is quite important and boosts the research that we done in the last years. Okay, and finally, I would like to thank you for your kind of attention, and I'm open to questions or comments you may have.
Thank you so much, Professor Fortunato, for this very inspiring presentation, and also for the proverb from Africa. It's very, very motivated. What did you say? And very true. Do you have any question from the audience? If we have, you can raise your virtual hand. We have already a question from our colleague, Professor Kavoulakis. So, George, the floor is yours.
I think Giannis Kalakatos comes first.
No, I cannot see. I cannot see any.
Just applause.
I have, first of all, wonderful stuff. Thanks a lot. I have two questions. The first one is you talked about stability. Could you tell us a few more words? I mean, stability with respect to what? Chemical reactions, or what kind of mechanisms destabilize these?
Both chemical reactions, because as you know, this type of metal oxides, they are used on for gas sensors, especially because they interact a lot with the atmosphere and to some species. And we test chemical stability and also electrical stability. We perform both.
I see. And the second question is, we all know that in many body problems, the effective dimensionality of a system plays a crucial role. Do you take advantage of this? I assume that these are quasi two-dimensional systems, right?
Not exactly, because, for example, for these metal oxides, of course, this is a surface. Everything happens at the surface, of course, but the thicknesses we are using are between 20 and 50 nanometers. I guess this is not exactly 2D, but they are, the interesting point is that they are completely amorphous. This type of materials, they are amorphous because also we grow thicker samples, and they are always amorphous, and they present very high mobilities, because in this particular case, since we have, they are ionic, I can say ionic semiconductors, the conduction mechanism is not affected by the disorder, because the conduction is through the s orbitals, not at the sp orbitals, as it is for covalent semiconductors. That's why it is very easy. Even when we start, even for us that, we work with amorphosilicon over the years. The group start the work, we start to work with amorphosilicon applied to solar cells. This was the beginning of the group. And after that also we start to use amorphosilicon to TFTs. And the amorphosilicon, the mobility is around 1 square centimeter per volt per second. No way to achieve higher values, because it's amorphous. And when we start to work with metal oxides, even without optimizing the material itself, we start to achieve mobilities between 30 and 40, even without optimization. And maybe we were lucky, I don't know, but it was very easy, and also that's why it was so fast. Usually when you start something inside your laboratory, until these new results or this new application moves to the industry, it will take some time, because you need to optimize the process, you need to do a lot of things. In the case of metal oxides, this was quite fast, because the first TFTs appear in 2004, and you start to have real applications in 2010. Only in 6 years, which is quite fast. But you start to have applications inside the industry, especially for mobile phones with high resolution. Of course, when we purchase a mobile phone or a computer, what we have is the final brand. I don't know from where it is the display, from where it is the microprocessor, but and in some cases we are using devices that even we don't know the type of technology that is behind. And in some of these high resolution mobile phones, for example, the technology behind is based on metal oxides. But maybe it's not truly 2D materials.
Okay, thanks a lot.
Thank you, George, for the question, and Professor Fortunato for the answer. We have a couple of questions from the chat. Let me read the first one from our colleague Dimitris Tsikridis. Thank you for the excellent presentation. There is increased interest for recycling and recovering of metals from electronic devices. How metal oxides can help towards this goal?
Yes, metal oxides, of course, if we are talking about electrical conductivity, this is always more difficult, because we have also transparent conducting oxides. Of course, the resistivities, the maximum resistivities we can achieve in some cases are 10 to minus 5 ohm centimeters. And of course, silver, the resistivity 10 to minus 6. It is hard to compete. Nevertheless, for some specific applications, and maybe not using metal oxides, but for example, using this new process that I shown at the end, we are using now this laser-induced graphene. We are able to transform the surface of a material directly into graphene, and graphene has a very high conductivity. And in that case, and this was already, we published this already, we are able to transform cellulose, the surface of paper, directly into graphene, just using a laser process. And in that way, we are not using metals. We don't need to use metals to have these electrodes. And this is carbon. And this carbon over carbon, and the problem of recycling doesn't exist, because we are using carbon over carbon. Even our body, the majority is carbon. So I guess for using these new approaches of laser-induced graphene and other processes, in that we don't need to use metals, because of course we are facing this huge problem related to electronic waste and all these type of things, and we need to find alternatives. Of course, some of the ideas that I gave you today is not the solution for all the problems we are facing in our world, but for some specific applications, why not? We have the tools and they are working quite well.
Thank you so much for the answer, and thank you very much, Dimitris, for the question. Another question from our colleague, Professor Dimitris Christakis. I don't know, Professor Christakis, you are with us. Do you want me to read the question, or you can direct your question directly to Professor Fortunato? What do you prefer? Okay, I'm going to read it. I cannot hear you. So the question from Professor Christakis, Elvira, is the following. What is the social economic impact of transparent electronics? Give us a picture of the future.
Very easy. I have a picture in my computer, but now I cannot find it. But imagine the number of mobile phones we are using in the world. I'm talking about this place, only this place, where this was the first application transparent electronics. Imagine the number of mobile phones we are using in the world. Imagine the number of the computers we are using, the number of televisions. I guess we don't have this is the biggest sector of applications. These numbers are quite high because mobile phones, computers, and televisions. In all of these devices, we are using displays. And for all these displays, we are using metal oxides for each transistor that is behind the pixel.
Professor Christakis, we cannot hear you. Probably you are facing, and you are not muted. It seems your audio connection is a little bit problematic.
Do you hear
Yes.
me now?
Yeah, very well. Go ahead, please.
It is very impressive. I'm very impressed in general with following you in your talk. But I want to put only one more question from the many you have raised. My question is that we people, I'm a mechanical engineer, and the impression I have about transistor is that it's a power electronic device. It is usually used in power electronics. Now you named only information devices that transfer information and not power.
Yes, not power. I'm talking only about like a MOSFET. Is a thin film transistor. It works like a metal oxide field effect transistors, only for information, not for power applications.
And let me make one comment, maybe, okay, I will do it. You give the impression of entering the, yeah?
This is just the figure that I would like to show concerning the impact of these, because some of the question was related to that. So here you have some numbers. So the market size until, and also until 2024, and the growth rate for these in this area is incredible. It's not for this specific application, and in this specific area, the impact is not a problem because it's quite high. Okay, this was the figure that I would like to just to show you.
Thank you very much. Thank you.
You're welcome.
Thank you very much, Professor Christakis, for the question and the comments. You have a lot of greetings and thanks from Ioannis Kaliakatsos. I would like to say that this collaboration with Professor Fortunato with the New University of Lisbon has been started many years ago through the organization of some summer school, but it's already is continuing with a new project about shared facilities in printed electronics together with Professor Fortunato and Manolis Kimakis. So this shows how the communication and participation in these events, in conferences, in summer schools helps and facilitates the collaboration. And this is important to collaborate, communicate, and participate in such an events or any events in order to share ideas. I have just a moment. There is one more comment. Thanks to you a lot and best to 2022. Do I have a time just for one question, Professor Fortunato?
Yes.
You mentioned something about applications of perovskite materials within your field effect transistors. And since always, this is something that we admire, you are starting everything from fundamental research and you are moving towards the market. I would like to ask you, how are you going to deal with the recycling of such a devices regarding the lead content of these perovskites? And moreover, my question is like, how much is affected the performance of your transistors if you move to lead-free perovskites?
Yes, this is still a problem we are facing. Yes, is like the indium for TFTs, for metal oxides, and lead for perovskites. Usually the performance of both devices on these metal oxides and on perovskites, they need to have these components. Of course, we are working, and we have even an European project, not for TFTs, but for solar cells, using perovskites without lead. Of course, the efficiency and the electrical performances are much lower. Nevertheless, the amount of lead that is used in these type of devices is very, very low. This is why, and sometimes also this is a little bit strange, that even the European Commission is approving projects on perovskites with lead. In one hand, lead is not forbidden, but it is advised not to be used. But also the European Commission is approving projects using lead in the composition. But the amount of lead is quite small. Nevertheless, also in our lab, we are working on perovskites without lead, but since for this, in the particular case of TFTs, so this is a little bit a new area, we want to exploit perovskites not only for solar cells, but also for other applications. At this moment, we want to optimize the device even using lead, and after that, having like a reference TFT, having a reference perovskite with lead, try to reduce the lead and add other compounds and try to achieve and optimize the device. Also, what I present today is quite recently, so we are also now it is not yet published, but also we succeeded to develop also thin film transistors using perovskites without lead.
And the performance is lower because in the solar
The
cell,
performance is lower. Yes,
okay,
this is
thank
one
you.
of the problems.
And that's another question that I have is regarding your X-ray, the X-ray dosimeter that you use. And I would like to ask you, what is the thickness of the active layer regarding the X-ray detection that you are using?
But for the TFTs itself.
Yeah. Yes,
it's always the same. I don't have here now the values, but as I mentioned before, the thickness of the semiconductor is between 10 and 50 nanometers maximum.
And this means that it's compared to the perovskite X-ray sensors, that we need something that, you know, a lot of microns in order to place them as an X-ray detectors. However, the high mass number they are characterized. In this case, you are telling me that, you know, the metal oxides, they have only two.
Maybe we are making a confusion. We are not using our TFTs for detect the radiation.
Okay.
Now we are using these electronics because they are not sensitive to the radiation.
Okay.
On the screen, you see.
Okay, excellent. So this
for the electronic part is not. We are not. They are transparent to this radiation.
Excellent. So this could be another another collaboration that we can have together here in Crete to build, you know, the perovskites as a detectors, and you are going to build the electronics that they are not sensitive to these X-rays have something different. Okay, nice.
Yes, correct.
Okay. So the meeting just finished because I can see Dr. Rogdakis has just arrived. So you and Manolis Kimakis, you lost 1 hour of a meeting, but Kostas will review, you know, whatever has been discussed.
Hi, Kostas.
Hi, so we had another meeting for a MERS project.
Yes.
Yeah, no.
That's why
I was at the beginning.
We saw you there. Okay, no problem.
Okay, so I would like to thank Professor Fortunato for this honor. Hopefully next time you will be in Hellenic Mediterranean University together with us in order to share your knowledge and your motivation. For me, it's very important that I can see a small country, a poor country, as Greece it is, how big things and how big achievements, you know, they can be inspired and be generated, you know, from few people that they have the motivation. I think that the example of Professor Fortunato for us as a university, as a country, is quite clear. We would like to thank you so much for this opportunity and honor. And I also would like to thank all the participants for the questions, the participation. And I would like to say, looking for Professor Fortunato's graph about the people and how the field effect transistors, they have been developed using metal oxides. I can see the name of Anthopoulos, Halig, Professor Fortunato, and also Munz, Ellen Munz. So Ellen Munz will be our next speaker next week here in the Sci Cafe. I will share the invitation with all of you, and many thanks and Happy New Year and all the best for 2022. Thank you. Obrigado. Obrigado.
Obrigado. Okay.
Obrigado.
Thank you, Elvira. See you soon.
Okay, bye-bye. It was a
Bye-bye.
pleasure. Okay,
Bye.
safe. Bye-bye.